So, half I omega square is the kinetic energy of this body for an observer who is located somewhere here. These days, many students keep asking me how to revise rotational motion chapter. So, I think that rotational motion is a big pain point when it comes to preparation of JEE. I thought I will do few videos to bring some conceptual clarity in this particular chapter. So, this is the first video in this series, and I will highlight a very important point which can help you in understanding many questions. So, I will clarify one doubt using this simple problem. Suppose this is a pendulum. There is a massless rod, it is a rigid rod, but it is not having any mass, and to this rod there is a sphere that has been welded. The sphere has been attached to the rod. Mass of the sphere is m, its radius is r. From the point of suspension O, the center of the sphere is at distance L, right. So, it is a simple pendulum, nothing else. Now, what I do is, I just push this pendulum bob, I just push this ball so that its center acquires a speed v. I push the bob and the center point acquires a speed v. Now, I want to ask this question. Immediately after I push the bob, its kinetic energy will be equal to half mv square. This is first option that I am giving to you. V is the speed of the center. It is just hanging. I have just pushed it, and immediately after the push, the speed of the center is v. Can I say that kinetic energy of this thing is half mv square? That is first option that I have given you. Kinetic energy of this thing can be written as, this is my second option, kinetic energy of this thing can be written as half I omega square, where I is the moment of inertia of this pendulum about this axis, the axis passing through O perpendicular to the plane of this diagram. So, kinetic energy of this thing can be written as half mv square. Is this true? Kinetic energy of this thing can be written as half I naught omega square. Is this true? Or I am giving you third option. That kinetic energy of this thing can be written like this. It is half mv square plus half ICM omega square. Here ICM is moment of inertia of this bob about this axis passing through its center of mass. In this third expression, ICM stands for moment of inertia of this bob about this axis passing through its center of mass, and in these two expressions omega stands for V by L. So, I have given you three options for writing the kinetic energy of this object. Immediately after I push it, its center is moving with speed v. Now, I am asking which of these three is the right expression, correct expression for kinetic energy of this object. Please do think for a moment. Think for 5 minutes in fact, and then look at what I am saying. Students, first one may appeal to many of you that it is correct. This object has been given a velocity v, and what's wrong in writing half mv square as kinetic energy? Actually, you can write half mv square as kinetic energy of a body only when each and every particle of the body is moving with speed v. When you push the bob like this, in this case, each and every point of this bob is not moving with speed v. I hope all of you understand that this whole thing is going to rotate about point O, and this, for example, this particular point is going to move in a circle like this. The radius of this circle will be L minus R. This particular point is going to move in a circle of radius L, this particular point is going to move in a circle of radius L plus r. So, all points are not having same speed. All the points definitely are going to have same angular speed, no doubt about it. So, speed of this particular point will be omega into this length, L minus r. Speed of this point will be omega into L, which is given as v. Speed of this particular point will be omega into L plus r, distance of this point from point O. In this case, actually this rigid body, I am so sorry, actually this rigid body is having a pure rotational motion about this fixed axis, no doubt about it. Each and every point is going in circle. When a rigid body moves such that its each and every point goes in circular path and centers of all circles lie on a straight line, then we say that it is in pure rotation. It is rotating about a fixed axis. So, here also all the particles are going in circles. Of course, their radius of their circular paths might be different, but they all are having same angular speed. They are going in circular path. Such a motion is pure rotational motion. In this case, we cannot write half mv square as kinetic energy because of the obvious reason that each and every point is not having same speed. What about the next two options? I think with this discussion only, all of you have understood that this one is definitely correct. This one is certainly correct because I can consider this thing to be a rigid body which is in pure rotation about this axis. Pen is the axis, this pen is the axis. So, this when a rigid body is rotating about a fixed axis, its kinetic energy is half I omega square, where I is the moment of inertia of the body about the axis of rotation. So, if I naught stands for moment of inertia about this axis, then this whole rigid body is rotating about that axis, and we cannot go wrong if we write that kinetic energy is half I naught omega square. That is perfectly all right, beyond doubt. What about the third option? What do you think about the third option? अभी भी pause करके थोड़ा सोच के बता दूं. Fact of the matter is that third option is also correct. Fact of the matter is that the third option is also correct. Yes, 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 yes. Well, motion of this particular body can be picturized in two ways. One way I have already indicated that this is the axis of rotation and each and every particle of this body is going in circle about this axis. So, we can say that this body is in pure rotation about this axis, no doubt about it. It is in pure rotation about that axis. But then any general motion, any plane motion of a rigid body can also be described as combination of two motions. I repeat, any general motion of a rigid body can be described as combination, superposition of two motions. One is spin about center of mass, rotation about center of mass, add to that, superimpose to that the translatory motion of center of mass. So, we think that a body is rotating about center of mass and then the center of mass is translating. You combine these two things and any motion of a rigid body can be understood. If I throw this bottle in air and it starts from this point and finally lands here in this position or this position, this whole motion can be understood as combination of two things. One, I will assume that there is an imaginary point in this bottle known as center of mass. That center of mass moves on a parabolic path like this and the whole bottle was rotating about that particular point center of mass. So, if initially it is like this and finally it is like this, I can just think that about center of mass, the bottle has rotated like this. So, while the center of mass is translating, the bottle is rotating about center of mass. If you combine these two things, any motion can be understood. That is the most important concept. So, if I go by that approach, how will I write the kinetic energy of this body? Center of mass is translating. So, due to translational motion of center of mass, there is a translatory kinetic energy in this body. Half mv square is there, no doubt about it. And if somebody is located here at the center of mass of the body, does he see any spin? if you are located, if you are an observer sitting over here, do you see any rotation of the body about center of mass? Can you see that? Yes, it is there. Yes, it is there. Students, it is there. I will draw a diagram to make it clear. Initially, this pendulum is somewhat like this. Let us assume that after some time it goes to this position, after some time it goes to this position, and after some time it goes to this position, so on and so forth. It is rotating, okay. So, if there is an observer located here at the center, if you ask him, where is this point A? He or she will say that yes, point A is just below me. This observer finds that point A is just below him. But after some time, this observer sitting over here, if you ask him, where is point A? He will say point A is to the right of me. Earlier he was saying that point A is at somewhat below me. Now he is saying that point A is to the right of me. After some time, if you ask this observer, where is point A? He will say point A is above me. So what does he see? One observer was looking at point A, point 1 was apparently below him, then it somehow moved to right of him, then it moved above him, and finally, when you ask this man, where is point A? He will say point A is to the left of me, and after some time he will again say that it is below me. So, from the perspective of this observer, can you see that point A is rotating? Can you see? So, fact is, when this pendulum makes one rotation to this observer, to this red colored observer, point A also makes one full rotation. Point A is here, then it is to the right, then it is at the top, then it is to the left, then again it is below him. So, by the time this pendulum makes one rotation, an observer sitting at the center of the ball finds that point A has also made one rotation about him. So, yes, if there is somebody located here, he or she will see that this body is actually spinning about this axis. Yes, I hope you have got it. So, if there is an observer over here, he will say that yes, this body is spinning about me. So, with respect to center of mass, when there is an observer at center of mass, there is a spin, and as I explained, that omega is same as this omega. So, in the reference frame attached to center of mass, if there is an observer sitting in the center of mass, he will say that this body has a kinetic energy of half ICM omega square, where ICM is moment of inertia about this axis, pen is the axis. So, half I omega square is the kinetic energy of this body for an observer who is located somewhere here. And then due to translation of center of mass, there is another kinetic energy term half mv square. When you add these two, you get the actual kinetic energy of this body. So, this thing is also the correct expression of kinetic energy. I leave it to you to prove for yourself that these two expressions are exactly same. You can prove that these two expressions are exactly same. For that, what you need to know is parallel access theorem. If you know that, you will be able to show that these two expressions are exactly equal. So, students, the key learning point is, if there is any general motion of rigid body, it can be understood as translation of center of mass plus rotation about center of mass. And in this kind of situations, you may miss to see the rotation about center of mass. Be very careful. There is a definite rotation about center of mass of this body. And if you can find an axis which is fixed and body is in pure rotation about that axis, then of course you can write kinetic energy as half I omega square about this axis. In many cases, in many problems, teachers do teach you how to find instantaneous axis of rotation, and if you are able to find the instantaneous axis of rotation about that particular axis, half I omega square is the kinetic energy, that is all. Okay. In this case, this is the axis of rotation. At every instant, this is the axis of rotation. The body is in pure rotation about that axis. But the same motion can also be described as translation of center of mass plus rotation about center of mass. Any motion of rigid body can be described like that. So, this is the point that I wanted to emphasize in this particular video. Hope you have liked it. If you have liked it, don't forget to press the like button. Please do share with your friends. That will be a great thing for me. Goodbye.